Okay, today we're going to talk about 2.4 modeling with quadratic functions. And really this is taking graphs and then writing equations for them. So we've went through where we've actually had equations and we've graphed them. Now we're going to go the opposite way. So quick reminder, the three different forms of a function of quadratic functions. You have standard form, y equals ax squared plus bx plus c. You have vertex form where they actually give you the vertex. Y equals a times the quantity x minus h, quantity squared, plus k. Your vertex in that case is equal to hk. And we have intercept form, y equals x minus p times quantity x minus q. And that is not the quantity squared, so please get rid of that. All right. So, I don't know why I do that, but x minus p times x minus q. And in that case, you are actually given the vertex, the intercepts, the x-intercepts there. So maybe something like this, where this would be p and that would be q. Okay, and then in vertex form, you're given the vertex of your parabola, your hk value. All right, so three different forms there. Okay, and so when you're looking at a graph, really, you're going to either pick vertex form or intercept form. Standard form is kind of your all-around general purpose form, and vertex form and intercept form are really the types you can look at a graph and maybe come up with an equation based on the given information. So when I look at, say, this graph over here, I note that they give me the minimum here, which happens to be my vertex, and that vertex has an x value, which we call h, and a k value, which we call, or a y value, which we call k, so our hk. So I am going to choose vertex form here, and I can write that equation, y equals a times x minus 5, that's my h, quantity squared, plus k, or 7. Now notice, we always, whenever we're writing an equation, we want our input and output features, our x and our y's, or at least one of them, and then we don't want any other variables. So h was replaced, k was replaced, but a has not been replaced. One other quick note, when you're looking at all three of these forms, these a's are all the same a. They all are the exact same. Okay. So when I'm looking at this form, I need to be able to get a. Okay. And so I could do that by, if I had one input or output. If I had an input or output besides my vertex, I could calculate a because I could substitute that value in. When looking at this graph, I note that they give me one other input output. They give me an input of 1, an output of 20. So x is 1, y is 20. So what I could do is I could plug in 20 for y, 1 for x, so substitute those values in for x and y, and then calculate my a value. So that gives me 20 is equal to a times negative 4 squared plus 7, okay, or 20 equals positive 16a. So let's get rid of that little negative sign there. Okay, so negative 4 times negative 4 is positive 16 times a, all plus 7. So 16a, if I subtract 7 from each side, would equal 13. So 1a would be 13 over 16. Okay, so then my equation, if I rewrite it, I would have y equals 13 over 16 times x minus 5, quantity squared, all plus 7. There we've got it. Okay, so let's go ahead and move on to the next problem here. We have a graph now, and you look at it and you actually have some intercepts here. Okay, so we have the x-intercept at 2, 0, another x-intercept at 7, 0. You're also given a y-intercept in this case at 0, 11.2, or another xy value. So looking at this, they give you a p and they give you a q. They don't give us the vertex. There's no coordinate down there. So really, we'd want to use intercept form here. Okay, and so looking at it, we'd have y equals a times x minus p, or x minus 2, times the quantity x minus q, or x minus 7. And once again, we have that square there. That should not be there. Okay, so get rid of that. Okay, and it's kind of an ugly looking 7 there. Holy moly. All right, fix that up there. Okay. All right. And so now if we want to find our a value again, we have to plug in our input, our other input and output. So we have an input of 0 for x and an output of 11.2 for y. And substituting those values in allows us to calculate our a term. That gives us -2 and -7, or positive, oops, got ahead of myself in thinking there. Okay, -7, which ends up being 11.2 equals 14a, and so a is equal to 11.2 over 14. Kind of an ugly fraction there, so what we'll do is we'll call that a is equal to 11.2 divided by 14, 0.8. Okay, so a being a 0.8, we have y equals 0.8 times x minus 2 times x minus 7. That is our equation for that parabola. Okay, so what we can do from there now is we can take a look at this graph, and the same graph, and you'll be asked to find the average rate of change. And so it says, what is the average rate of change over the interval in which our graph is decreasing and in which is increasing? So what I put is here is remember slope. So really what you're looking at is you're looking at a point from where our graph is increasing. So let's say our graph has to exist in only positive realm here, and let's say it actually goes from 0 and it goes to 7. All right. So I am going to put a domain on this graph. I'm going to say our domain. I'm going to put a rule here when x is greater than or equal to 0, but less than or equal to 7. So in other words, find what is the average rate of change over the interval in which our graph is decreasing and increasing when x is greater than or equal to 0, so starting here, and less than or equal to 7. So in other words, between here and here. Okay? Or the other way to think about it is to say, go ahead and erase this, is to say in this picture, we are going to ignore this little piece above here and all of this part of the graph over here. Okay, so we're going to focus on the decreasing piece first. Okay, so the decreasing piece is where we start here, and we're going to go down, and we're going to hit right there at the vertex. That is where it's decreasing. Okay, and so decreasing, what I want to do is I want to actually find a slope of a line that would actually go from this point up here at 0, 11.2, oops, and would intersect our vertex. So you're finding the slope of that line there. Okay, so if you think back to linear equations. All right? So that would mean I'd have to find change in y, delta y, over change in x, or delta x, if you recall that. Okay, or The other way to think of it is y2 minus y1 over x2 minus x1. All right. So I can look at these. Well, I can see right here I have like if I want to call this x1 and y1, but unfortunately down here I don't have a point yet. So if I were to say, well, that's going to be my x2, y2, well, I don't have those yet. So I'd actually need to do a little calculating there. So if you recall, our vertex is equal to the opposite of b over 2a. Well, that's great if you know standard form of this equation. So remember, we wrote the equation just a minute ago over here, 0.8 times x minus 2, x minus 7. So same graph. So if I were to take that equation, y equals 0.8 times x minus 2 and x minus 7, I could multiply it out and put it in standard form. Or I could recognize, well, I at least know my x value. My x value is taking the average of my intercepts. So it has to be directly in between here. Okay, so if I look at this and say, well, p and q, if I take p minus q and, excuse me, p plus q, and divide it by 2, that is actually going to give me my axis of symmetry, which is going to be the h value of my vertex. Okay, so I could go ahead and substitute the pieces in here. P is 2, so 2, q is 7, divided by 2, that's equal to 9 over 2, or 4.5. So 4.5 is the h value of my vertex. Well, if 4.5 is my h value, to find my k value, all I have to do is substitute it in. So k is equal to y equals 0.8 times, instead of x, I'm going to put 4.5. So I'm going to substitute 4.5 in for x, minus 2. 4.5 minus 7. And that gives me 0.8 times 2.5 times negative 2.5, which is also equal to, you do the calculations, just negative 5. So that is negative 5. That's my k value. So I know my vertex now. And I also, let me go ahead and divide this up here, I can also substitute some values in. y2 and y1 now. I have y2, it's negative 5. I know y1, it's 11.2. I know x2 is 4.5. And I know x1. x1 is 0. So doing the math, negative 5 minus 11.2, negative 16.2 over 4.5, which ends up being negative 3.6. So my rate of change, where my graph is decreasing, is 3.6. Negative 3.6. Now, if I'm looking at increasing, well, increasing, I'm going to have to change up my color here. Let's highlight it here. So, choose a different color. Increasing is from my vertex up to 7, 0. And so with that, if I'm actually calculating where it's increasing, let's go ahead and switch my ink color here, and we'll keep it the same as the highlighter. And I'm going to do, once again, delta y over delta x. It's just this time it's going to be increasing. Notice it was decreasing, gave me a negative slope. Increasing should give me a positive slope because my line is going up here. Whoops, really went off the track there. So let's try that again. Okay. Boy, I'm having a hard time drawing a straight line. It's part of the problem on my tablet here. Let me try this. There we go. Much better. Okay. So I'm looking at that line right there. All right. And so really delta y over delta x, let's kind of go through this a little faster here. So we're going to have y2 minus y1 or negative 5. And this is x1, y1 this time. Okay. And minus 0 and 4.5 minus 7. Okay. And so looking at that, you end up with negative 5 over 4.5 minus 7, or negative 2.5. And that gives me a slope of 2. All right, so it's increasing. My rate of change is 2. So which one has the greater rate of change? Well, decreasing has the greater rate of change. Okay, whereas increasing or decreasing has a slope of negative 3.6. When it's increasing, it has a slope of 2. One other piece here for this lesson, we talk about first and second differences. So first and second differences in this situation, if you remember back to slope in algebra, we talked about change in y over change in x. Well, here, notice x is increasing by 1 every time. Now, if we look at our change in y, well, we got plus 2, plus 2, plus 2, plus 2, and plus 2. This is called a first difference. Oops, it's supposed to be a plus. Okay, and so a plus 2. So notice our slope is 2 over 1. And our y-intercept just happens to be when x is 0, so we get 11. So we easily wrote our equation, y equals mx plus b, and that would be our equation. That's linear. Well, this has a first difference. Well, if you're dealing with quadratic, if you want to find out if a pattern's quadratic, notice your x is going up by 1 again every time, or going up by a constant, in this case 1. Well, notice my difference here. This one actually is minus 5, minus 3, minus 1, plus 1, plus 3, plus 5. Well, not the same there, so I'm going to keep going. Difference here is plus 2, plus 2, plus 2, plus 2, and plus 2. This is a second difference. And hopefully this pattern wasn't tough to figure out. I mean, look, you're squaring x every time. Okay, but a second difference tells you that in terms of what type of graph you have a second degree or a second degree polynomial versus a first degree. So this was a first degree, x to the first. Well, this one is a second degree, x to the second. If you had a third difference, it'd be x to the third. Okay, and in fact, this just happens to be the equation. Now, it's not always that easy to figure out there. But this is a second difference. All right. So what I'm going to do is I'm going to go ahead and have us move on to an actual problem. It says, decide if the data represents linear or quadratic, then write a function to model it. Well, I'm going to first look at x's and make sure x's are going up by the same every time. They're all going up by 1. And then I'm just going to calculate the difference. Plus 3, plus 5, plus 7, plus 9, plus 11. Okay. And plus 2, plus 2, plus 2, and plus 2. So it happens to be a quadratic. Okay, second difference. So it's a quadratic. All right. So with that, what I'm going to do is I'm going to have us actually go to Well, all right. What I've done is I put that information into a table here. So I put our x1, our x values, -2, -1, 0, 1, 2, 3. Our y values, 2, 1, 2, 5, 10, 17, 26, 37. I'm in Desmos here, so I put those into a table. Okay, well that table allowed me to plot the points, so you can see the points here, at least most of them. If I were to zoom out, you can see the rest of them. Okay, so we've got all of our points, and looking at, looking at these points, you can actually see that it kind of looks like it's quadratic, but if I were to use my equation here, y sub 1, that takes my y sub 1 values, and I use my little similar key. You can find that on your keyboard here. Down. Right down here. Okay, and ax squared plus bx plus c, notice that you have to put x1 so it references all your x1 values. Okay, and when I do that, it allows me to, if I click on it, it allows me to see the parabola. It does kind of a line of best fit of linear regression here. It tells me my r value, or r squared value, is 1. It does have residuals, which we'll get to at another time. We're not going to worry about that right now. That's actually what this row is. It tells me how much it varies, which it doesn't vary at all. So my residuals are all at 0. That means it's a perfect pattern. But then it tells me my a term. My a is 1, my b is 6, my c is 10. So that means I have y equals 1x squared plus 6x plus 10. 1x squared plus 6x plus 10. So I'm going to go ahead and switch back here. Okay, so this equation is y equals 1x squared plus 6x plus 10. All right, and you can also use a graphing calculator to do that rather than Desmos, but it's so easy for me to show Desmos, and Desmos, quite honestly, is pretty easy to work with. The only problem is if they don't allow it on standardized tests or your SAT